Oh, hello there!
I'd argue that it was Ben Eater that popularised 8-bit computer building and made that style of computer building video possible. As you found your way to this video series, you'll probably be aware that 8-bit computer build videos are pretty done now. As a result, I'm going to attack this series a slightly different way and almost pick up where Ben Eater left off. The way I'm going to format each video is by giving a brief explanation as to how Ben designed the module for his SAP1, simple as possible one, and I'll add bits here and there to align it closer to how real computers do their thing. I've been working on this since 2016 as a bit of a passion project. I'm now at a stage where I feel confident that hobbyists, enthusiasts and the education space can really benefit from what I have to offer. I'm designing each module in kit form on solder yourself PCBs with a backplane so you can plug them all together exactly how you want to make fully customizable hardware to fully suit what you want. Fancy having a microcontroller with 10 registers? Go for it! Fancy having 2 addressable RAM modules, effectively doubling the amount of memory that you have? Be my guest, and want to see how far you can take it with only 4 bits on a program counter? Best of luck to you! As I explained before, each of these videos will have a go at building up Ben Eater's design for the given module. I'll give my best go at briefly explaining how it works, but I very much recommend having a look at his video just to make sure that you have a full understanding. We'll then analyse the design and potentially suggest some improvements of how we can closely align it to how real computers do their thing. By all means, feel free to follow along with breadboards and components that you already have, but as I say, I'm designing PCBs for each of the modules, so it really will be plug and play exactly how you'd like it. If that's something that you'd be interested in, please do let me know in the comments section. In terms of video layout, I quite like to go down rabbit holes and see where that takes us when I'm trying to explain something. So what I'll do is add a little context tracker on the side of each video, so hopefully it will be a little bit easier to follow along with my rambles. Let me show you what I mean. For this first video, let's make rocks count. First off, why do we need a clock? Well, electrons are really fast, like crazy fast.
I don't think you have any idea how fast I really am.
But they do still have a speed limit. This is one of the main things that limit how fast computers can actually run. And big tech companies are constantly coming up with new ways to harness this maximum speed, and even speeding it up. A computer is all about running commands one at a time, and as such, it needs a way to take note of this maximum speed that the hardware can run at. It does this by using a clock. Instead of keeping track of the time of day, this clock sits there ticking away at a set amount of times per second, and that's called the frequency. Much like a conductor, making sure that everyone stays in time and lets people know when everything is going to speed up or slow down, the clock is the conductor of the computer, telling everything when to execute the next instruction. There are 2 stages to our clock cycle, the prepare and the execute, a 1 or a 0. To represent this, we'll use a square wave. This is a very simple wave that is just a signal that goes up to 5 volts when we want everything to execute, and then back down to ground when we're ready to prepare the next instruction. Manufacturers of processors set their clock speed a bit slower than the hardware can actually manage. This is acting as a safety margin so that it doesn't risk the hardware falling over itself. You might have heard of a thing called overclocking. This is increasing that clock frequency closer and closer to the actual speed that the hardware can run at. Now, while this can increase performance, it can make things run a little bit too fast, which results in hardware falling over itself. We're going to do our best to walk that fine line between making sure that we're getting the most out of our hardware and not tripping over ourselves. There's a lot more to talk about clocks, but that's basically what one is. So how do we make one? Ben Eater does a great job of explaining all of this in incredible detail, and I most certainly will not do it justice. As such, if you want to learn more, I really recommend going to have a look at his video. I've put the link in the description. but I'll give a brief overview of how it works and I'll build it too. It uses resistors to charge up and discharge capacitors at a set speed. That speed depends on the size of both the resistor and the capacitor. At set thresholds, the output of the 555 timer will go high or low. We can use this mechanic to make all sorts of timing circuits like A-stable, an oscillating square wave, or monostable, a nice clean pulse. Let's first look at a use case for a monostable circuit. The simple tactile switch. Here I've just got one of those tactile switches hooked up to an LED. In a Newton's cradle, when you lift one ball and drop it, the force when it makes contact with the other ball transfers to the ball at the very other side, and that is the ball that then swings up. In a tactile switch, the same mechanism is true, however there's nowhere for that excess force to go. So instead of another contact swinging another way, all that happens is those same two contacts bounce on each other. I've just hooked up this thing called an oscilloscope, which is used to measure voltages across time so that you can see a full graph as to what's happening. Using the oscilloscope, we can fully demonstrate what I mean by this Newton's cradle effect. You can clearly see that it doesn't happen every time I press the button, but it does happen, and when it does happen, it could send two signals to our electronics, and that could throw everything off as well. We can fix this by using one of these 555 timers that I talked about earlier. Here's me building one right now. The schematic for my circuit is here, and at the moment it's heavily based on Ben Eater's design. Now you can see that the circuit is complete, and that every time I press that button I get the exact same square wave. No bumps, no second pulses, no anything like that. Just one clean square wave that we can use throughout our computer. The next type of clock signal we'll take a look at is the A-stable circuit. This uses internal switches called transistors to switch between charging and discharging when certain thresholds are met. This results in an alternating square wave at a frequency that we can set using various sizes of resistors and capacitors. It's called A-stable because the output signal isn't stable. It's changing all the time. You're going to get sick of me saying this, but the circuit is based off Ben Eater. It works perfectly, and you can see a really clean square wave that comes off it. This will be used for the clock signal for our computer. This video so far has been nothing new really. I've basically just been copying what Ben Eater did, and I did promise something different, so let me try some actual original content. I spoke earlier about the hardware speed limits compared with the clock speed and the safety margin that manufacturers add in. Here's what that actually is in action. All I've done here is bunched up the two timing circuits, and then I've added in this chip called an AND gate, and this compares two inputs and outputs true if both inputs are also true, or 5 volts or 1, same things. Its name is the 74LS08, and every chip has a datasheet attached to it. Here's the one for the 74LS08. What I'm doing here is adding a second channel to the oscilloscope so that you can measure two signals at the exact same time. The two signals that I'm measuring is first off the yellow one, which is the signal directly out of our A-stable 555 timer, and we have the second signal, which is the blue one, which is the signal that comes out of the 74LS08, the AND gate. We can see that these signals look pretty similar, but let's take a deeper dive into this. While this oscilloscope is not particularly high precision, it does show some pretty good data that we can actually correlate with the datasheet. We can measure this transition period here, and it looks to be about 21 nanoseconds. That's 21 times 10 to the negative 9. The way that the signal moved was from low to high, so let's have a look at that value on the datasheet. We can have a look at the name of this parameter here that says TPLH. That means the time propagation from low to high. The maximum amount of time that this can take, the worst case execution time if you will, looks to be about 27 nanoseconds. That's pretty close to our 21 nanoseconds that we saw on the oscilloscope. I'm happy with that value. As we can see then, this piece of hardware takes 21 nanoseconds to go from low to high. And if we ask it to go any faster than that, it won't be able to. All of the internal electronics will just fall over itself and you'll get undefined results. And that is what we mean when there is a hardware speed limit. Every chip ever used, or any piece of electronics, will have one of these hardware speed limits. Some might be very much smaller than others. This one is actually quite slow. But when setting the clock speed, we need to take these figures into account, so that nothing can fall over. If you've watched Ben Eater's series, you'll know what the last thing is to do. Just add a few more circuits so that we can switch at any time between astable and monostable clock. I'll just do that really quick. While I'm doing that though, I will just remind you that I'm not here to reinvent the wheel. Ben Eater has very much made that. I'm just here to build on it. This was the first module, probably one of the simplest, and so there really isn't much to change from Ben Eater's original design. With that said though, I really hope you enjoyed this first video of the series. In the next one, we'll take a look at upgrading Ben's 8-bit register to a 16-bit transfer register for a separate data and address bus. Thank you so much for watching, and I'll see you there. Just one more thing before I do go. Earlier I spoke about a PCB. Well, this is a little teaser of one. Neat, clean, and probably available soon. See you.